Okay, one last video for class 14. I sure packed in a lot. Ambition was too high here. But here's an example where we're going to do a centrifugal blower. And this isn't actually really all that much different from like the example, I don't even remember which one it was, like example 3, I think, where we had velocity triangles, but we'll do it anyway. So we have a centrifugal blower. I'm kind of almost thinking this is radial. So there's like a leaf blower, maybe? I don't know. 15 centimeters, sure. And it's got a blade width of 6.1 centimeters, right? So this thing, from a side view, let me pause this for a second and come up with the side view. All right, so I adapted the slide a little bit. And so anyway, this is what it kind of looks like right here. You can see that there's dimension B1 right there. So the R1 is the 15 centimeters, and the B1 is 6.1 centimeters. And so then the outlet of this thing, which is right up here, that's the R2, is going to be 30 centimeter radius, and it's the blade width is 3.4. So that kind of explains it. It was hard to tell from up here. Disregarding any losses and assuming the tangential components of the air velocity at the inlet and the outlet are going to be equal to the impeller velocity at respective locations. All right, so that's kind of okay. I guess if in a perfect situation that might be the case. Determine the volumetric flow rate of the air when the rotational speed of the shaft is 800 RPM and the power consumption is 120 watts. Also determine the normal components of the velocity at the inlet and the outlet of the impeller, right? So we're going to have like a radial velocity in and out right there, and that's what they're calling it the normal components, but might call them the radial components as well. So they're saying they're kind of giving us sort of a premise for where to start in here. So let's move on to this. And they told us a couple things. They told us that they were going 800 RPM, so that's a good place to start maybe. And we'll take 2 pi over 60 and say we have 83.78. That doesn't seem right. I think it's right though. And I guess I said therefore no. Okay, whatever. I'll do my FBD of this. And we're going to be spinning this way, and we're causing it to spin, so the torque must be moving in that direction. And this is a momentum diagram. I should also point out, remember, in many of the problems, we were looking for the reaction torque, but here we have an applied torque, so it's a little bit of a different type of problem, that there's a motor that's somewhere driving and making this thing spin. And we will go ahead and use their little designations right here, that this is going to be m dot v2 in the tangential direction. We'll also have a normal direction right there. So that's the v2 normal direction. And here's the v1 normal direction. And here is our m dot v1 tangential direction, as we put out to there. This is air. So for the density, we need to use the ideal gas law. And so we're going to go ahead and use this. Normally, notice that's a vacuum. It's less than atmospheric. And by the way, they didn't tell us, but so this is sort of an assumption that we made, but there's no reason this would be 95 kilopascals gauge. So that must be absolute. So that's the kind of the thought we have. They could take the ideal gas law and find that we have the pressure divided by the gas constant for air and the temperature. So we're going to say that this is 95 E3 to get it in newtons per square meter. And we have this is, I'm going to write 287. I think there might be a decimal place I'm missing onto there. And then the absolute temperature is going to be the 20 plus 273. So we get 1.130 kilogram per cubic meter. So that helpful. That's good. We can also find the torque. We can find the applied torque here by taking the power and dividing by the angular velocity. So we have 120 watts, or a Newton meter per second, and dividing it by 83.78. And what we're left with is 1.432 Newton meters, and that's being applied to the impeller. So the velocities that we're going to have, they told us the velocities here are going to be, so V1t is going to be equal to omega R1, or 83.78, and the inside radius is going to be, this is 1, so it's going to be 15 centimeters, or 0.15 meters, and 12.57 meters per second. And V2t, and I'm writing, and I guess I put commas in there. Omega R2, 83.78, and what did they say? They were 30 centimeters, so this should be 2 times that, so 25.13, 2 times the other one. And these are low enough that we don't have to worry about compressibility issues in here. And we might notice that the m dot that we're going to need later on, just as a note, m dot is going to be density times the volume flow rate, and that's really what we're looking at. We're looking for the volume flow rate, right? So we would determine the volume flow rate, or maybe the mass flow rate, or whatever. So up above, taking a look here, we could write out our main equations. The sum of the moments is going to be the sum of the outlets, R m dot V, and minus the inlet, R m dot VT, right? We could also use Euler's equation, Euler's turbine equation. So up above, we see that's a negative torque. And here, for the outlet, we're also going in the negative direction, so we could go with that. Did I want to do that? Yeah, I think I do. I'm a little concerned by it. I think I'm going to be okay. I didn't write it down my way, but anyway, I went negative R2, and the m dot is going to be density times the volume flow rate, and that's going to be times V2t, and I'm going to go minus, but now this also needs this minus, but it needs to be minus because this 2 is also going in the clockwise direction. I picked a minus here because it's the clockwise direction, and this is also minus, so it's minus minus. So we're going to have R1 times density volume flow rate, and V1, 1t. All right, so I can solve for my volumetric flow rate, and what I said it was going to be, I think all these minuses are going to cancel out onto the thing. Yeah, I think we're going to be fine there. And so I'm going to take the torque and divide it by my density times my R2 V2t, and that's going to be minus, so the minus, so this one is still minus, sorry, 1 V1t. I think I got that right. So we're going to take our 1.432 and divide by our density, 1.130, and then multiply that by our R1, which we said was 0.3, 30 centimeters, so 0.3, 25.13 from right here, minus our 0.15, and that's going to be the 25.13 No, sorry. Yeah, no, I got it right. Okay, no, yeah, 25.13, and then this is going to be times the 12.57. And I'm going to get a volumetric flow rate estimated at 0.2242 cubic meters per second, right? So I could find now the mass flow rate if I wanted to, but this is really what we were asking. And then notably, the normal velocity is going to be equal to the volumetric flow rate divided by the area at 1, which is going to be the band, right? It's going to be the band that would be the thickness right here. So remember up over here, let's take a look at that. That's going to be this. So this is 1. Okay, so it's going to be that width times the circumference right here. So it's going to that circumference times this thickness right there is going to be the area of the inlet. So it's going to be 2 pi, and then the radius was 0.3 there. Yeah. And then, yes, no, 0.15. Sorry, 0.15. But now we need the thickness of the thing, which was 6.1 centimeters. 6.1 centimeters. So that's going to be 0.061. And we end up with 3.899 meters per second. And I'm done. So I'm tired. I'm tired with these examples. We do the same thing here and get the area 2, which the only difference is this would be 0.3, and then this would be 3.4 centimeters right there. So we get something that's very close, actually, 3.498 meters per second would be the normal. So I'm done. That was the last example for class 14, and I'm not going to make this many examples next time. It's just too many examples. Ambition, whatever.